All right, in this section we'll be looking at exponential functions. Notice it says exponential functions are functions having a variable in the exponent. We say y equals f of x equals b to the x, really we just need this part here, is an exponential function if b is some constant, so a number like 2 or 3, some fixed value, where b is greater than 0, so it can't be negative. It can't be 0 either. And b does not equal 1. Well, if you have a base of 1, 1 to any power is just going to give you 1. And so that would be why it would be that way. So go ahead and look at our exponential functions here. Notice all of them have a base that's greater than 0 and not equal to 1. And let's see. Let's look at this last one, g here. Be careful here. The base is actually just the 6. It's not negative 6. So basically you're taking 6 to the 2x plus 1 power and then you're applying the negative. And so that is considered an exponential function. Notice each of these. Notice here these are backwards. The variable is supposed to be in the exponent. It's switched. What's wrong with the second one there? Notice your base is a negative number. This time your base is everything in the parentheses. And then finally, the problem with the last one is the x. It's not supposed to be a, oops, I have that wrong. It's the base. The base is supposed to be a fixed value greater than 0. It can't be a variable. And so none of these are exponential functions. Whoops, I got ahead of myself there. On number 1 there, you should be able to put that into your calculator and get 2.639. Basically, you're just going to put in the 2 and then the caret symbol to the 1.4 power and hit enter. You should go ahead and try number 2. You may be able to figure it out. All right, so you should get 0.334. So the way you would do that is, there's actually a couple of ways, but the most, probably the easiest, most common way people use the e on their calculator is using second, and then you have an ln button that's got an e to the x power right above it. That's why you have to hit second, and then you put in the number and you'll get the answer that I just gave you. All right, so now let's look at how we graph exponential functions. It turns out that it's not too difficult to find points for an exponential function, especially the more basic functions. So let's go ahead and plug in 0 here. f of 0 would be 2 to the 0 power. Anything 0 power is 1. If we plug in a 1, f of 1 is 2 to the first power, which is 2. If we plug in 2, well, let's see, 2 squared is 4. If we plug in 3, 2 to the third power, that'd be 2 times 2 times 2, and you would get 8. So let's go ahead and plot these points. So you can see that we've got this thing pretty much figured out on the right side. It's going to look something like this. Notice it's shooting up really quick. What's going on the other side of the x or of the y-axis when x is negative? Let's go ahead and plug in a negative 1. So I'm going to go ahead and plug that into the function. You get f of negative 1 is 2 to the negative 1 power. Well, remember, by definition of negative exponents, that's 1 over 2 to the positive 1 power. We talked about how negative exponents lead to reciprocals. And of course, that's, 1/2, 1 over 2. Or let's go ahead and plug in negative 2. You get f of negative 2 is equal to 2 to the negative 2 power. That's going to be 1 over 2 to the positive 2 power, which is 1/4. So let's go ahead and plot these points. And you can see what's happening. This is similar to what was happening when we were graphing rational functions in the previous chapter. This curve is going to get closer and closer, but it's never going to get to the x-axis here. If you put in -3, you'd get 1/8. If you put in -4, excuse me, you get 1/16, and so on. You'll get closer and closer to 0, but you're never going to get there. And so there's an asymptote here at y equals 0. Now, notice on the right, this function is growing really fast. The y values are increasing really quickly. This is an increasing function, notice, because left to right we're always rising, but also this is what we call an exponential growth function. This is the type of function we use to model things that grow quickly. Well, coronavirus right now is causing some real problems with people getting sick and dying, but anyway, all to say the numbers are growing exponentially. And at some point, we look for them to level off. But in the beginning, we have exponential growth. All right, so our domain here is -infinity to infinity. There is no leftmost or rightmost point. Notice on the right side, it's going up fast, but it does continue to go to the right. Now for the range, be careful. There is a lowest point. In fact, we never get to 0, so it's right above 0. There is no highest point, and so 0 to infinity would be our range. And we said our horizontal asymptote is y equals 0. Horizontal asymptotes turn out to be an important feature of exponential functions. Now, what if I were to ask you, what's the key point on this graph? Well, it's 0, 1, which is our y-intercept. So basically what we're going to end up, well actually let's go ahead and do another problem and then we'll do some generalizing. So on the next problem here, notice my base is a fraction, 1/3. So this is, let's see, let's go ahead and pick some values here. If we plug in 0, anything to the 0 power, that's 1. If we plug in 1, 1/3 to the 1 power, or to the first power, is 1/3. If we plug in 2, I'm going to go ahead and do that one. You get 1/3 squared, so we're just going to multiply 2 1/3s. You multiply across, you get 1 times 1 over 3 times 3. That's going to be 1/9. All right, so let's go ahead and plot those points. And you can see what's happening as x gets bigger and bigger. In fact, if you put in 3 as an x value, you would get 1 over 27. So you get really close to 0, but you're never going to get there. So you can see we have an asymptote again at y equals 0. Let's plug in some negative values. If we plug in -1, we're going to have 1/3 to the -1 power. Now it's been a while since we've done one like this, but basically what we do is we flip the fraction and change the exponent. So it's 3 to the +1 power, which is just 3. So you might want to go ahead and try f of -2 real quick. When you plug in -2, you're going to get f of -2 is equal to 1/3 to the -2 power. We'll flip that and make that a +2. So this is just 3 squared, which is 9. So let's go ahead and plot those points. And you can see what's happening on the left. This thing shoots up. Or you could, coming from left to right, you would say it's falling down rapidly. All right, so this is, excuse me, a decreasing function because it's always decreasing. And this is what we would use for a model for exponential decay. Notice in the beginning, this function's dropping really quickly, and then it takes a long time. In fact, it never gets to 0, it just keeps approaching it, but it takes forever to level out. All right, so our domain is still all real numbers. Notice the range is again the same. It doesn't quite get below or get to 0. So going from lowest to highest point, there is no lowest point, but it gets closer and closer to 0, but it'll never be there. So 0 to infinity, of course it goes up forever. And our horizontal asymptote is y equals 0. And again, if I asked you what the most important point was, that would be that point 0, 1, the y-intercept. So what we're going to end up doing is finding 3 points when we graph these types of functions. It'll be the y-intercept and a point on each side of the y-intercept. All right, let's move on to the next slide. So we're going to go ahead and summarize now. So if you have a function f of x equals b to the x power, again, we call this an exponential function. The base has to be positive, greater than 0, and it can't be 1. And when we graph these, we just discussed how we're going to use these 3 x values. Basically, we're using the y-intercept, and we're choosing a point on each side right next to the y-intercept. So you'll always start the same when you graph an exponential function that's in this basic form. And we'll choose x to be -1, 0, and 1. Next it says y equals 0 is a horizontal asymptote, and that's what we were seeing. If our base is greater than 1, like when we graphed 3 to the x power, we had a function that was increasing. I'm just going to give you an example here. If you have y equals 2 to the x power, you're going to have an increasing function that looks like that. Again, asymptote at y equals 0. Now notice here the base is between 0 and 1, so it's a number like a half or a third, 4/5, something between 0 and 1, but not equal to either of those. So as an example, we have y equals 1/2 to the x power, and that would look like this. So basically it has a very similar graph, it's just going in the opposite direction. The one on top represents exponential growth, the one on the bottom would represent exponential decay. Alright, so let's go down below here, and it talks about transformations. So we're going to take the things we were doing earlier in this course, and we're going to do them with these exponential functions. So it says, recall if we're given some function f of x, we've got these different transformations. If we have y equals our function plus some number, then we're up k units. So I'm going to show you these with the example here. In this problem, f of x is the square root of x. So f of x plus k, that would be y equals the square root of x plus, I'm going to use 2 for k. And so notice in this problem, this would be the graph of y equals the square root of x moved up 2. You may recall the graph of the square root of x looks something like this. I call it the ET function. All right, so the next one, y equals f of x minus k. That would be the graph of f of x moved down k units. Oops. So that would be this one here, and it would be the graph of y equals square root of x moved down 2, for example here. For the next one, y equals f of x plus h is going to cause a shift h units left. So as an example, notice if you plug in x plus 2 here, that's basically the idea. We would get y equals the square root of x plus 2, which we know causes a shift to the left. This is a horizontal shift. These are the ones that are backwards. And similarly, on the next one, an example would be y equals the square root of x minus 2. And so this is a shift to the right. The next one says y equals minus f of x is a reflection over the x-axis. And that's our most common type of reflection. It's where you have the minus out in front of the function. So in our case, it would be y equals minus the square root of x. And that would be this graph that I just graphed a minute ago, reflected down. It would look like that. And on the last one here, that would be a reflection over the y-axis. So that would be y equals the square root of minus x. That would be my example. And that would actually go this way. We would be reflecting across the y-axis here. All right, so let's go ahead and do some problems now using these ideas. All right. Let's say I think I'm going to stop right here and I'll do a second video.